Good day and welcome back to our third part of the discussion on tangent planes and linear approximation. In the previous videos, we've introduced tangent planes from the computational perspective and then more recently seen how we can use them to approximate values. In this video, we're going to take a slightly different perspective on that same idea of approximation, and to do so, we're going to use things called differentials. So to get started, I want to remind you kind of how we encounter them and use them in Calculus 1. And then we will extend the idea to Calculus 3. And our whole kind of goal, what it is that we are working towards, is I want to somehow approximate the value of the function f at some point a plus a little value dx. I want to say this is approximately equal to what? So I'm going to think a plus delta x, where in this case delta x is representing kind of a small change in our x value. And what we would like to know is for this small change, where we're going to let dx be equal to exactly that change, what can we say about the function value at that point? That is, if we trace up to the curve at a plus delta x, the output would be f of a plus delta x. And what we're trying to approximate is that desired value. And we're going to use the tangent line to help us approximate it. So the tangent line is now drawn in red. And what I'm going to indicate is a line going up to the tangent line. I will call that distance dy, and if you go all the way up to the curve, we'll call that total distance here, change in y. And what we want to observe is that change in y, the actual amount the function changes as you go from f of a to f of a plus delta x, is approximated by just going the amount of change we see with dy. And the key idea is as follows. So for the function y equals f of x, which we have pictured in blue, dy is equal to f prime x dx. Think exactly what you would do with a substitution. And what we want to observe is that our delta y that we've indicated, the true change in y, is approximated by dy. So if I want to know the function value at a plus a small change in the x value, that is, I want to know precisely what is the output associated with that input, how I can get there is to start off with the function value at a, and if you have that function value at a, this kind of height above the x-axis, how much further up do you need to go to get to that point? Well, we could approximate that by saying let's just go up dy. And that's the big idea of how we use differentials when we are in Calculus 1 to approximate the value of a function. If you know f of a, you can use the differential dy to approximate the value at some small distance away from a. So let's now go ahead and introduce differentials for a function of two variables. If you have the function f of xy, we think of the differentials dx and dy as being independent variables. That is, quantities we can substitute an input for. And what they are going to do is represent a small change, much like the dx above represented a small change. Then the differential dz is going to be defined as follows. dz will be the partial of f with respect to x at xy dx plus the partial with respect to y at xy dy. And the connection I want you to make is, at least if we look at this first term, it's very similar to that idea of a differential we had back in Calculus 1, But instead what we are now doing is taking into account the fact that we have a function of two variables, so we need to have terms corresponding to each of those partials. And similar to Calculus 1, the idea is that the true change in a z-value should be approximated by this differential dz. That is to say, for xy close to AB, where the function value at AB is something you can compute by hand quickly, the function value at xy is approximately equal to that function value at AB plus that small associated change. So plus dz. And it turns out that this is really just putting a slightly different spin on the idea of linearization. So this is the same idea as a linear approximation. So let's go ahead and investigate a nice concrete example. For z equals 5x squared plus y squared, what we would like to do is determine as xy, our input, changes from 1, 2, think of this as the easy value to compute, to 1.05, 2.1. Let's compute two things. First, we'll compute the true change in outputs, and then we will see what dz is, this differential, and hopefully observe that it does approximate that actual or true change. For the true change in z, we simply want to think, what are the associated outputs to the two inputs, and then we'll calculate their difference. The function f of xy would be represented by 5x squared plus y squared. So we can immediately observe that f of 1, 2 will be 5 times 1 squared plus 2 squared is 9, the simpler value to compute. And we can also compute f of 1.05, 2.1. This will be 5 times 1.05 squared plus 2.1 quantity squared. And if you want to go through the arithmetic, that's perfectly fine. Or if you substitute this into a calculator, you get 9.9225. And the difference between those two outputs tells us the true change in z values. So that would be f of 1.05, 2.1 minus f of 1, 2. And the difference is going to be that decimal 0.9225. And now what we're going to do is pretend that we don't know this true change in z values, and we are going to come up with our approximation using the differential. So that is, we're going to find the associated dz. And in order to do so, we need a few partials. The partial with respect to x is 10x. The partial with respect to y is 2y. And then we also need to know what is our small change in x and what is our small change in y. And if we compare our points 1, 2, and 1.05, 2.1, what we can note, to go from 1 to 1.05, dx would be 0.05. Similarly, to go from 2 to 2.1, dy, the change in y values, would be 0.1. So dx is 0.05, dy is 0.1. And from our previous definition of dz, it's going to be defined to be f sub x at that point 1, 2, the value that's easy to compute, times dx, plus f sub y at 1, 2, times dy, the small change in y. And the quantity we would like to determine is, what is dz when x is equal to 1, y is equal to 2, dx is equal to 0.05, and dy is equal to 0.1. And as a reminder, this notation, when we put a vertical bar and we subscript it with values, those are the values that need to be substituted in. So working from left to right, f sub x of 1, 2 is 10 times 1. dx is 0.05. The partial with respect to y at 1, 2 is 2 times 2. And dy is 0.1. This gives us 0.5 plus 0.4, which is equal to 0.9. So as a reminder, this differential dz is determined by multiple quantities. This point where the function is easy to compute, in our case 1, 2, and small changes you're making in the x and the y direction. Once you have calculated out the dz, remember the desired kind of outcome you're looking for here. We have this observation that the true value of the change in z is approximated fairly closely by this differential dz. And this completes the material related to differentials, and once again we're at this perfect position for you all to practice some examples. So in Canvas you can find an associated worksheet, and what I would suggest doing is spending some time working through those examples, and in the next video we'll go through one of the key problems related to differentials. So stay tuned and take care.